Hey there, chemists. Welcome to our next lesson in the electrochemistry or redox chemistry unit. Today we're going to be focusing on what is called a half reaction. And so let's go ahead and just dig right in. So we're provided an equation here, and I want you guys to balance this equation. Feel free to pause the video and attempt to balance this equation. And if you take a look here, you'll notice that we have, according to how we already know how to balance equations, we have zinc, Zn, we have one zinc on our reactant side, we have one zinc on our product side. In terms of our iron, we have one iron on our reactant side and we have one iron on our product side. And so what we notice here is that this equation is actually already balanced, right? It really just requires a 1-to-1-to-1-to-1 ratio. And so what I want to tell you is that this actually isn't already balanced. And we are actually seeing an imbalance due to charge. Notice that we have an overall +3 charge on our reactant side and an overall +2 charge on our product side. And so what we're going to talk about today is how do we balance these reactions according to charge. So let's go ahead and dig into another equation. So let's go ahead first here and assign an oxidation number to each of the elements present in the equation. This should start to become second nature to you. We've been practicing this all week. So in terms of assigning oxidation numbers, we should start with the easiest, which is going to be anything that exists in elemental form. So in our reactant side, we have pure elemental sodium, and on our product side, we have pure elemental aluminum. Moving on from there, we can use our rules that we have, right? For example, group 1 ions are always going to be +1. That's going to help us over here assign the Na a +1 charge. We can also, from that, determine our charge of our oxygen. We have 2 sodiums. Each are worth +1. Therefore, our 1 oxygen must be worth a -2, which actually is another rule, right? Oxygen is almost always a -2. So we're going to go ahead and assign a -2 to our oxygen in the reactant side. And from there, we can determine the charge of our aluminum. We have we have 3 oxygen. Each is worth -2 for a total of -6. And we have 2 aluminum, so we get 2x - 6 = 0. Each x is worth +3. Now, why is this going to be considered a redox reaction? Or how do I know just by looking at this that this is deemed a redox reaction? Well, by definition, a redox reaction is going to be a reaction in which the electrons have been lost or gained by species, or a reaction in which there is a transfer of electrons. So what evidence do we have? Note that we see that our oxidation number of sodium changes and the oxidation number of aluminum changes, which means that there is a movement of electrons somehow between aluminum and sodium. So this is a redox reaction because electrons are being lost or gained by Al +3 and Na 0, okay? And again, we want to specify Al +3 because that is on the reactant side of our equation. The things that are going to be transferring, or the species that are going to lose or gain electrons, are always on the reactant side. The result of that loss or gain is what we have on our product side. Next, we want to go ahead and determine which species was reduced, which was oxidized, and which was our spectator ion. So in order to do that, let's start with spectator ions. I like to take those out right off the bat and kind of eliminate them from my problem. So again, a spectator ion is anything whose charge does not change. And the only species which charge does not change in this reaction is going to be oxygen. So we're going to go ahead and eliminate oxygen from our thoughts. It is our spectator ion, okay, because the charge does not change. So oxygen because the ox number or the charge doesn't change. All right, next, let's go ahead and write down our mnemonic device. I always find it's helpful to have it on our sheet of paper. So in order to determine oxidation and reduction, we're going to think of oil rig, or Leo says GUR, whichever you prefer. Oil rig oxidation is loss, reduction is gain. And for those of us that are still struggling with, determining if there's a loss of electrons or a gain of electrons, something else I do like to write on the paper is that a loss of electrons is going to result in your charge or your oxidation number becoming more positive, or we're going to see an increase. And a gain of electrons means that my oxidation number is becoming more negative, or we're going to see it decrease in value. So let's go ahead and determine reduction first. Reduction is a gain. We should be seeing the charge go down. And so aluminum goes from a +3 to a 0. And that's going to be a gain of electrons or a reduction. Okay, so our species, which is reduced, again, you have to specify that it's aluminum +3, not just aluminum, because pure aluminum, elemental aluminum, is a product. So Al +3 is reduced because it gains electrons and the charge decreases. Okay. Next, we're going to be looking at the oxidized. Well, Na goes from 0 to +1. That's going to be a loss of electrons and an oxidation. Again, our loss of electrons mean our charge is increasing. So Na, because it loses electrons and charge, is going to increase. From there, which species is the reducing agent and which is the oxidizing agent? So reducing agents are going to be what makes reduction possible. Now, oxidation and reduction go hand in hand. We can't have one without the other. So in order for reducing to be possible, a species must be oxidized. So our reducing agent is always going to be the species that is oxidized. And so our species that was oxidized was Na. So Na, because without Na losing electrons, okay, Al +3 can't gain electrons. And so Na helps us by losing electrons to make reduction, so that reduction is possible, okay? From there, oxidizing agent, similar idea here. Our oxidizing agent makes oxidation possible. Oxidation can't happen, losing electrons can't happen unless there is something there to gain those electrons. So this is going to be our species, which is reduced. So again, Al +3, because without Al +3 gaining electrons, okay, Na can't lose electrons. Amazing. Now, we need to take a look at each of these processes individually. I want to look at the aluminum losing its electrons. I want to look at the sodium gaining, or I'm sorry, the aluminum gaining its electrons, the sodium losing its electrons. And I want to look at those on an individual basis. And so we end up writing or creating what is called half reactions to help us investigate those on their own. And a half reaction is literally what it sounds like by definition. It's a reaction, okay, that represents just the oxidation or just the reduction in a reaction, okay? And so let's go ahead and separate our reactions from above into just their oxidation and into just their reduction. This is going to help us in the long run by allowing us to balance by charge. So let's go ahead and take a look at oxidation versus reduction here. So our half reaction for our oxidation, remember in our reaction here, oxidation, the sodium was oxidized. So sodium went from Na solid, okay, to Na plus 1 aqueous, okay? Our reduction reaction went from aluminum plus 3 aqueous to aluminum solid, okay? So from there, right, according to mass, these are already balanced, but according to charge, they're actually not. And so what's the major issue that we're seeing here between these two reactions? Well, take a look at your reactant side. For sodium, we have a 0, and for Na or for aluminum, we have a plus 3. And for our product side, we have a plus 1 and we have a 0. So we actually have an imbalance of charge being a plus 1 versus a plus 3 in these different reactions. So according to mass, why are these balanced, but they're not actually? We have different amounts of charge in each half reaction. So how are we going to fix this? Well, let's first talk about why this is problematic. Remember, oxidation and reduction go hand in hand. So the species that is being oxidized is giving its electrons to the species that's being reduced. So in this reaction, sodium is giving up how many total electrons? Sodium is giving up just 1 electron. But how many electrons does aluminum have to gain? Well, aluminum is a plus 3 becoming a 0. It needs to gain a total of 3 electrons. So we're running into problems because we don't have equal numbers of electrons. And the number of electrons that we lose must be equal to the number of electrons gained. So let's just jot that down. Number of electrons lost must be equal to the number of electrons gained. So before we can do that though, what we do whenever we're writing half reactions is we're going to add electrons into our reactions to balance our charge out, okay? So we are going to add here a plus 1 electron to balance our charge. Why am I adding it to the product side and not the reactant side? Well, our reactant side has a 0 charge, so we need our product side to also have a 0 charge. Sodium is plus 1, therefore we need to balance it out with a negative 1 to make it overall neutral. You can also think of it as, hey, sodium is losing an electron, and therefore the electron is separated away from sodium. For our next reaction, our product side has a 0 charge. We need our reactant side to have a 0 charge, and therefore we're going to add 3 electrons here to balance out that positive 3 charge. These are our half reactions. So now what I want to do is I want us to talk about how we're going to use these half reactions to determine how to balance our half reactions. So we have 6 steps for balancing using half reactions. Step number 1, assign oxidation numbers to all elements in a reaction. Okay, so if you're given a full reaction, first thing you're going to do is assign all of the oxidation numbers, just like we have been. Step 2, okay, determine which species were reduced or oxidized. And this isn't new. This is, again, everything we've been doing up through this point. So steps 1 and 2 is something that we've already done. Step 3 is where we start to see something new. This is going to be split into half reactions. Okay. Step 4 is going to be to balance each half reaction separately, okay, by adding electrons. So everything that we've seen here, 1, 2, 3, 4, those are all things we've already done. So now how do we use our half reactions to balance our reaction by charge? Well, again, as I mentioned, the number of electrons added, or I'm sorry, the number of electrons lost must be equal to the number of electrons gained. So we need to take a look at how our electrons are balancing out. So you're going to use coefficients to make sure the number of electrons in each half reaction matches. Okay, and so what that means, let's go up top and take a look. On the reaction we were working on here, our oxidation has just 1 electron, our reduction has 3 electrons. So in order to balance this out, we're going to multiply our oxidation reaction by 3. And now we know that it's going to take 3 sodiums to provide enough electrons for 1 aluminum to be reduced. Okay? Last thing that we want to do is we want to rewrite this as what is called a net reaction. So we're going to rewrite as a net reaction. What is a net reaction? A net reaction means taking our 2 half reactions we had and combining them into one more reaction. So I was thinking, like, in terms of like talking about net profit or something, we're talking about everything all together again. So let's go ahead and piece everything together. On the reactant side, we have 3 sodiums, 3 electrons, and 1 aluminum plus 3. So let's go ahead and write that out. We have 3 Na solid plus 3 electrons plus Al plus 3. And then on our product side of our reaction from above, we have 3 Na plus ions, 3 electrons, and 1 aluminum solid. So we have 3 Na plus 3 electrons plus Al solid. Okay? Now, in a net reaction, we can eliminate anything that matches on our reactants and our product side. So the only thing that matches is our electrons. We're going to go ahead and eliminate those, and our final equation is 3 Na solid plus Al plus 3 becomes 3 Na plus Al solid. So why are the electrons not going to be included in our overall net reaction? Because the electrons match on both sides. We're going to go ahead and pause here since this video is already 19 minutes. I do apologize about that. We will practice with the reaction we started with in the beginning of class on Monday. Have a great weekend, guys, and I'll see you guys later.